Good day to you, grade 11 learners. Welcome to the discussion on junior examinations for geography grade 11. Right, we are going to go through this junior examination task, and we are going to elaborate on how best we can respond to the given set of questions, and also try to elaborate in an effort to assist you to prepare you for the upcoming examinations as a guide. Right, so as usual, we understand our paper is a full paper, which is having 150 marks, which are supposed to be attained in 3 hours. That's the setup of the junior examination for grade 11. So without wasting much time, we need to go to our questions. And the guide to the questions, we understand we have question number 1, which is based on the atmosphere, which is 60 marks. And we have question number 2, which is based on geomorphology, which is also 60 marks. That is our section A theory. Then we have, as usual, our section for geographical skills and techniques, which is question number 3 in section B, with a total of 30 marks. So that gives us a grand total of 150 marks. Right, we go to our first section, which is section A, question number 1, the atmosphere. Right, the first question is saying, the A in the figure above is, we are looking at a situation here where we want to analyze this kind of air movement. We are seeing that the air is coming from the upper atmosphere and going towards the ground surface. So we are saying this is our upper atmosphere, and we are seeing the air sinking towards the ground. This is typical of what happens with the formation of our anticyclones. Over the interior, we're looking at the color area high pressure cell. We have dominance of sinking air. So when you're having sinking air in this instance, what is the correct response? The air is subsiding. Subsiding air is the same as sinking air. And then the opposite, if the air is rising, we say it's ascending. Right, then number 1.1.2, the A at A is the A at A. If we look at A here, we are seeing that one arrow is going to the direction of the other arrow. So if you're having this instance of A coming together, this is what we call convergence. Right, so what you must remember is when we have a high pressure cell, we have convergence in the upper atmosphere. The air comes towards each other, and as the air comes together, it ultimately has to subside, like what is suggested by B. And as you see, when the air gets to the ground, it tends to diverge. So in the upper atmosphere, there's convergence, then the air sinks, and then ultimately it forms a high pressure cell where the air diverges. Right, so for number 1.1.2, our correct response is A for convergence. Right, the A at B is dash and dash. The A at B, if you look at B here, what features are this air mass having? We see that this is air coming from the upper atmosphere. So in terms of the temperature, automatically this air must be cold. And if we look at its tendency here, this air has got a tendency of sinking. Air which sinks, it means it has got more density. So the implication there is, in terms of temperature, the air must be cold. Why? Because it's coming from the upper atmosphere. And also for the sake that the air is sinking, we tend to find that air sinks if it has a higher density. If it's heavier, then it sinks. So cold and dense, those are our two responses, and they are aligned at response C. Then number 113, at C, a dash pressure forms with dash rainfall. Right, at C, Let's look at C and analyze. We are seeing C here, close to the ground surface. What happens with C? We said when A is sinking, automatically it's going to create an anticyclonic system here. Or we're going to have the development of a high pressure cell. The high pressure cell develops because of the increased concentration of the air molecules because of the sinking air. So close to the ground, we tend to find that we have the development of a high pressure cell, which is an anticyclone. And in terms of the high pressure cell's relationship with rainfall, we talk about the Kalahari high pressure cell, which dominates over the interior during the winter season. And for the same reason, that is why we have clear cloudless skies during the winter season in most instances, because for cloud formation to happen, we need to experience a situation of rising air, not the opposite of sinking air. If air is sinking, it means there are no chances of condensation taking place, and ultimately the chance of precipitation being realized, they are almost zero. So in this instance, we are saying there's no rainfall there. So it forms a high pressure without a rainfall. So it's a high and no rainfall, which is response B. Right. Number 115 says the ocean current influence temperatures on the South African East Coast is D. If we look at the South African East Coast, we are looking at this side here. This is our western side, and this is our eastern side of the Southern African subcontinent. And if we check there, we see we have the Mozambique current. That is the one that influences the conditions over the eastern coast of South Africa. And the opposite on the extreme end is the Cold Benguela current, which also influences the conditions over the Western Cape. So here, number 115, we are saying our correct response is the Mozambique current. Right. Number 116 says the influence of the ocean current mentioned in question 115 on the East Coast is. How does it influence the conditions over the Eastern Coast? The reason why we have drier conditions on the Western Coast and we have wet conditions on the Eastern Coast is because of the influence of these ocean currents, which are experienced in the two extreme coastal sides of South Africa. So if we check in that instance, we are looking at the issue of rainfall. In this instance, we are saying it has a high influence. This ocean current here, it causes high rainfall on the extreme eastern coast. Places on the interior of the country have got a dash climate. Places on the interior, we're saying places which are inland. What kind of climatic conditions do they experience? They experience what we call the continental climatic conditions. Continental meaning to say we are having typical climatic conditions which are typical of inland places. When we talk about maritime climatic conditions, we are looking at climatic conditions in areas that are close to the water bodies where there is influence of the oceans. But in this instance, we are relating to conditions for places which are inland, which are far away from the seas and the oceans. Right, that was question number 1.1. Let's move on to question number 1.2, which is a matching column question. Right, seasonal winds that reverse direction between summer and winter, that is common understanding. We have the monsoon winds. So if you check your monsoon winds, they are typical of what we call the regional winds. They are regional winds, which are basically experienced in India. And the reason for their development, we are looking at the alternating temperatures during summer and winter between land and water. So there is also a shift in the pressure cells, such that the wind moves in one direction during a particular season, and they also shift to another direction in another particular season. That is what we call the monsoon winds. And when you look at geostrophic flow, a geostrophic flow, I think most of you must remind yourself that when you're looking at a geostrophic flow, it happens as a result of the balance between Coriolis effect and pressure gradient force. When we have PGF balancing with Coriolis effect, that is where we tend to have air that blows parallel to our isobars, which is not a norm in geography. Right. Let's look at question number 1.2.2. The side of a mountain where winds descends and warm up is the right. If you are looking at the side of the mountain where we have winds descending and also ultimately they heat up diabatically because of the descending, it is our leeward side. I think that is still common understanding. We have on the windward side, that is where the air is fed from. And that is where we experience the formation of clouds that produce rainfall on the windward side. But on the other side, which is the opposite, the leeward side, we tend to find that the air now is descending and it heats up adiabatically. That will give us the issue of typical backwinds in South Africa as a result of the air descending from the interior going towards coastal areas. Right, number 1, 2, 3, phone winds are also known as the phone winds. These are typical of regional winds. Right, I think there's need for clarity there also. You must distinguish between regional winds and planetary winds. There is a distinction there. Right, well, co-regional winds, we are saying they affect a relatively smaller geographical space, or they are winds which are known to affect a given smaller space, smaller geo space. And planetary, these are winds which are experienced on a wider scale. Our planetary winds, we find them according to the distribution of our pressure belts. We have the 0, we have 30, to the north we have 60 as an example, just to highlight our planetary winds. Right, these are our lines of latitude from 0 degrees the equator to around 90, which is the North Pole. I'm going to use the northern hemisphere. So we have our planetary winds, they are experienced because of the differences in pressure belts here. This is a high-low pressure belt, and this is a high pressure, and this is a low pressure, and this is a high pressure belt. So for this reason, we are saying air moves from high pressure to low pressure. And in that essence, there is an effect of Coriolis force that causes the wind to deflect. So as the winds deflect, we tend to have this belt here, a belt of planetary winds. Our planetary winds, they happen in 3, in the north and in the southern hemisphere. We have number 1, a belt of the tropical easterlies. Right, it's one example of our planetary winds. And number 2, we have the belt of westerlies. And also number 3, we have a belt of what we call the polar easterlies. So these are our planetary winds. They happen on a bigger scale, like from between 0 to 30. This is a belt of the trade winds or the tropical easterlies. And this is a belt of westerlies from 30 to around 60 to the north and to the south. This is a belt of the polar easterlies from 90 to around 60 degrees north and south. Right, so those are our planetary winds. Then when we look at our regional winds, we have, for example, the phone winds. They now affect a relatively smaller space. And for South Africa, we have typical of the back winds. These are regional winds. We can also talk of other regional winds like the monsoon winds. These are typical regional winds. Right, that was just a matter of trying to elaborate on the distinction there. But let's look at number 124. It says the rate at which temperature changes in the atmosphere with change in altitude is the the rate at which temperature changes in the atmosphere with changes in altitude. We call that the temperature lapse rate. The lapse rate. Right, wind that flows parallel to isobars in the upper atmosphere. We have talked about that. That is a geostrophic wind. A factor responsible for moderate temperatures along the coast. Moderate temperatures along the coast, they are as a result of the distance from the sea. We tend to find that the distance from the sea affects the temperatures of places which are along the coastal areas. Why? We have cool summers for coastal areas, and also we have warmer winters. Why? Because of the moderating effect which is brought by the ocean. So we have typical of maritime climatic conditions for such regions, and that is a factor of distance from the sea. Right, number 127 says factor responsible for decreasing temperature with height. When temperature decreases with height, that is the effect of altitude. Do not confuse between altitude and latitude. When we are talking about latitude, we are referring to the distance from the equator. That is latitude, if we are referring to it as a factor that affects temperature of a given geographical space. So the implication here is we understand that the sun's overhead position is around the equatorial region. And as a result, we tend to find that places around the equator, they are always warmer than places far away. If you check at 90 degrees to the north and the south, we have the northern pole and the southern pole. Those places are frozen. They are very cold. Why? Because the distance from the equator is extreme. We are having high latitudes there. And also it means the sun's rays have to travel for longer distances to reach those areas, which means the amount of insolation received there is ultimately going to be less. And also, if you check at it from the perspective of the sun's angle, the sun hits those places at a lower angle. The sun is lower in the atmosphere for places far away from the equator, and as a result, we have a lower temperatures. Right. Number 128, it says factor affecting the amount of solar energy received from the sun. It's almost the same. Latitude, like what we're discussing. Right, let's go to question number 1.3. Question 1.3 is based on the tricellular model of global air circulation. Our tricellular model of global air circulation, it has the polar cell from around 60 to 90, and it has the ferrule cell in between 30s to 60s. Then it has the Hadley cell from the equator to around 30 degrees. Right. The first question says, name the pressure belt at A. The pressure belt at A. What is this pressure belt here? It's at the equator. So the pressure belt at A is called the equatorial low pressure belt. It's equatorial low pressure belt. But give a reason for the formation of the pressure belt mentioned in 131. What is the reason? So what you need to explain here is there is a subpolar. So a subpolar is a high pressure belt. And as a result, A moves from the subpolar high pressure and converges at the equator. So A moves from subpolar high pressure and converges at the equator. At the equator. And at the equator, remember, there are high temperatures there. Because of the high temperatures, the air is heated. around that area. Due to surplus insulation, there's more heat or the shift there. And then as the air is heated, it rises. So basically that's what happens. We are seeing that there is a high pressure subpolar here. There's sinking air. As the air sinks, it is driven towards the equatorial region. The same happens from the other direction. The air comes, it converges here. After converging here, the air tends to rise. What facilitates the rising of the air is because of the high temperatures. The air is heated by the high temperatures and it rises. That creates this particular pressure belt. Differentiate the characteristics of A at B and C respectively. What are the features of A at B and C? Right. If we look at B, our B is there and our C is there. So at B, we are looking at A, which is coming from the polar. And if you look at here, C, the A is coming from the polar region. So what is going to happen there is at B, we have warm air. Warm and moist air. Warm, subtropical, high. So this belt is a belt of high pressure, subtropical, but it's a region which brings in warm and moist air to the polar front here. And what happens at C? What kind of air comes from C? This is cold and dry. Cold and dry air coming from polar region. So basically that is what happens there. We have warm and moist air feeding from this side, and we have cold and dry air feeding from this side. And for the reason that these two air masses have got different properties, one is cold in terms of temperature, other one is warmer. They cannot mix, so they tend to be separated by the polar front. That is where we have the polar front developing, which is a boundary which separates these two air masses because of their differences in their properties. Right. Then let's look at the A at B and C converges at D. Name the phenomenon formed at D. We have already explained that there is formation of a polar front. The two air masses are going to be split by what is called a polar front. Describe the movement and the pressure of the air at 30 degrees to the south. The movement and the pressure at 30 here. If you look at the movement, clearly there, you can see that this air is sinking. It's sinking, creating a high pressure. So we are saying in terms of the movement, it's clear the air descends or the air sinks. The air is descending here. So the air descends, that's the movement. Then looking at it from the perspective of the ground here, creates a high pressure. So the air descends, it sinks, and also it creates a high pressure. That is basically our response, movement and pressure. So movement, the air is sinking, and pressure, it creates a high pressure. Right, that was question 3.3.5. Let's go to refer to the following plan view and answer the questions. Name the wind at E. I think we have talked about that. E is a belt of westerlies. And explain the formation of the wind at E. Why do we have westerlies? Right, the first thing that you must note there, we are saying the air at 30 degrees flows towards 60. So we are saying at 30 degrees, we have the subtropical high pressure, and the air is going towards the subpolar low pressure. So the air flows from 30 to 60 because of pressure gradient force. Is being driven by pressure gradient. Coming from 30 is a high pressure cell and 60 is a low pressure belt. So air moves from high pressure to low pressure because of pressure gradient force. And what is going to happen? The Earth's rotation causes the wind to be deflected. In other words, we are looking at Coriolis force. Because of Coriolis force, the winds tend to be deflected. They tend to attain another direction, which is not a straight direction. So as a result, because of deflective effect, remember the Ferrell's law, winds are deflected to the left in the southern hemisphere and to the right in the northern hemisphere. So because of the deflection, winds appear to come from the west. Winds coming from the west, which are therefore named the westerlies. That's basically the picture of what you need to address there. Right, let's look at question number 1.4. Question 1.4 is a synoptic map. We can see that there's a low pressure over the interior, and also we can see there's evidence of a cold front, which is part of the mid-latitude cyclone, which is far down there. And also we can see we have our high pressure anticyclone on the eastern side. We also have typical of a coastal low pressure, which is somewhere there. Right, let's answer the questions. The first question is saying, name the lines on the synoptic map joining places with the same atmospheric pressure. That is common geographical understanding. Those are what we call isobars. Then determine the isobaric interval on the synoptic weather map. What we call the interval, we are looking at the difference between two isobars, the difference in pressure between two isobars next to each other. So if you can check between these two, this is 1024, this is 1020. If you find the difference there, you find that it's 4 hectopascals. And also if you try to check 16 to 20, again there is 4 HPA. So our interval is 4 hectopascals. Remember, do not leave units of measurement. Compare the pressure gradient at A and B with each other. The pressure gradient at A and at B. Right, if you are looking at A, or A is along this line, and B is along this line. So what's the nature of the pressure gradient there? At A, this is steep gradient. Steep gradient. Then we go to B. B is a general gradient. Right, those are our two. A steep gradient for A and a general gradient for B. Right, give a reason for your answers. Why are we saying it's steep and why are we saying it's a general gradient? For a steep gradient, isobars are close. close to each other. Here you can see that the isobars are close to each other along line A. But if you check here, why are we saying it's general? Isobars are far apart. So when isobars are close together, it implies that there is a steep gradient. There is sudden change in pressure, which means it is going to result in strong winds. But when the isobars are far away apart from each other, it suggests that there is a weaker gradient. And it implies that the type of wind that we're going to experience there is going to be light and variable winds, which are not ultimately for the sake of giving us strong winds. Right. So we need to look at the next part. The next question is saying, compare the pressure gradient. We have compared. The reason for your answer, we have given that there's a steeper gradient where there is isobars which are close to each other, and also where there is a spacing of the isobars, it suggests that there is general gradient. Then draw the weather station depicting the following information. Right, it says our temperature is 32 degrees Celsius, our dew point is 18 degrees Celsius, cloud cover is 1/4, our wind direction is southeast, and wind speed is 15 knots. We are supposed to draw a station model to summarize those weather elements as indicated by the question. So what you need to note here is when you are drawing your weather station, remember our circle here is supposed to accommodate our cloud cover. And what is our cloud cover? Our cloud cover is 1/4, which means we must try to make a subdivision of a quarter, and we shade only that fraction 1/4 of the total circle area. Right, that is our cloud cover. Then remember, when you are putting your temperatures, you just write them as absolute figures. You don't put the units on the weather station. You just write your maximum temperature or your air temperature is 32. You just write it like 32, no units. And your minimum temperature, you write it at the bottom, is 18. Then we want to figure out our wind direction. Our wind direction is determined by the direction to which our arm points from the circle. So where does our arm has to point to? Our wind direction is southeast. So southeast will point somewhere towards this direction. That is your wind direction. Then at the end of the arm there, you are supposed to put the feathers that represent the amount of wind speed in knots. And what you must always remember is for every one full feather is equal to 10 knots. So a half will be representing 5 knots. So if you're having 15, it means we want one full bar and a half. So we are going to draw the one for 10 knots. We are assuming that is our full, and then a half of that is going to give us 15. So basically we have addressed all the requirements there. Our temperature, maximum temperature is there. Our minimum temperature is there. Our cloud cover is there. Our wind direction is here. Our wind speed is given there. That is basically what you need to note and what you need to summarize when you're drawing the station model. All right, I'll give 2 reasons why this synoptic weather map is considered a summer map. Right, what do you need to check then? The indications on a synoptic map that give us an idea of the season. Right, what you need to check there besides checking the date, if there's a date for the map, is one of the obvious reasons that you can use. Check the date and see if the date is a date for summer month in the southern hemisphere, or if the date is representing a winter month in the southern hemisphere. But for the sake of our map here, You can also check, we have our date here. If you check closely, we can see that there is a date which is indicated here. It says South African Standard Time, 2011, February 19. So there is an indication here of a date. So if you look at February, we are saying this map is for February. February is basically a summer month in the Southern Hemisphere. So February ultimately gives us the indication that this is a summer map. And you must qualify your response. Don't just say the date, because if you say the date, what about the date? Explain to say that this map is for February, and February is a typical summer month in the Southern Hemisphere. Right. Then we'll also look at other evidence. We have a low pressure here, a low pressure over the interior. What causes this low pressure over the interior is because of intense heating, what we call the thermal, is called the thermal low pressure. So the thermal low pressure is ultimately experienced during the summer season. Why? Because that is where we have high insolation. And as a result of high insolation, we tend to find that the air which is immediately above the ground surface is going to be heated, and it becomes less dense and it rises. As the air rises, ultimately it creates a low pressure over the interior. Right. And also, if you check, there is also the issue of rainfall over the eastern parts. If you check these station models here over the eastern coast, you see that they resemble a lot of cloud cover. They are having so much cloud cover. Most of them, they're having 8/8, which is also a suggestion that we typically have cloudy conditions and rainfall during the summer season. We cannot experience these stations here over the eastern coast having so much cloud cover during the winter season. Why? Because we have the development of the Kalahari high pressure cell, which influences and gives dry conditions over the interior during the winter season. We typically have sinking air during the winter season than having rising air, which creates a typical situation of clouds and precipitation over the eastern coast. So you also check on that. And also, if you look at the location of the high pressure cell, this one here, the position, the high pressure cell is further to the south. What does that mean? We are saying these high pressure cells, how do they move? The South Atlantic and the South Indian high pressure cells, we said they move latitudinally with the shift of the ITCZ. So the implication is, if we are having summer conditions over the southern hemisphere, it means the sun is to the south of the equator. And at the same time, we are seeing the northern hemisphere will be experiencing winter conditions. Why? Because we are sharing the same sun. If the sun is further to the south, it means it's far away from the north. So the high pressure cells, they also tend to deviate their position with the change in the ITCZ, what we call latitudinal displacement of the high pressure cells. So as a result of the movement of the ITCZ further to the south, give us summer conditions over the southern hemisphere. The implication is also that these high pressure cells, they tend to move further to the south. So if you see the position here of the South Indian high pressure, it's further to the south. If it was winter, maybe it would have been somewhere there, adjacent to the land. But as it is summer, it goes further to the south. Right. And also the other evidence that you can also look at, check this cold front here, the mid-latitude cyclone. This cold front there is further to the south, which also suggests that it does not have a bearing on the Western Cape. We experience the coming of cold fronts over the Western Cape area of South Africa during the winter season. So this mid-latitude cyclone, if you check its position, it has no chances of it getting to approach the western coast there, because it's placed somewhere further to the south, which means it's going only to sweep over the ocean and does not affect the western coast of South Africa. Right. Those are some pieces of evidence that you can use for that map. Right. Then number 1.5 is talking about drought crisis in Southern Africa. Let's not worry about the text. We are all only worried about how to respond to the questions. Right. Define the term drought. What you must note there when you're defining terms in geography, you must address the basics. Do not force yourself to remember the definition as it is from the book or as it is from whichever source, but you must understand the basic idea of the concept and you must address it in your own words. So I can define drought as a long period of time with little rainfall. Or in some instances, no rain. Or also in some instances, below average. That is a drought situation. So when you're having a long period of time when there's very little rain or when we have no rain at all or when you're having rainfall which is beyond below the expected average, that is a drought situation. And remember, with geography, we say drought is regional specific, meaning to say what we can regard as a drought in one area might not be a drought in another area because we are looking at the averages. If we expect a lower average in a particular area, it means once we receive that minimum, we are not experiencing a drought situation because that is our expected according to climatic conditions of the area. But you tend to find that what is regarded as a drought situation in one area might be sufficient rainfall in another area depending on the climatic condition. That is why we are saying drought usually is regarded as regional specific. Right. According to the article, what caused the severe drought? Right. If we look into the text, it talks about a strong El Nino. That was the cause. Refer to the infographic and describe the impacts of drought on agricultural sector. Right. If you check on this, what is the implication? These are maize crops, and you see the implication there. So we are saying our crops are dying. And what is the implication? It means loss of income for the farmer. The farmer is not going to have a good harvest, and ultimately they are going to be affected economically in terms of their level of income. Right. Let's go on to the next part. Which drought interval in Southern Africa was the longest? Which drought interval was the longest according to the text? You tend to find that according to our statistics here, according to our indications of which drought interval in Southern Africa was the longest according to that question, it was the 2018 to 2021 interval. That's the longest interval that we experienced. Then what was the impact of the longest drought interval in question 1.5.4? The longest interval caused water shortages. There were extreme water shortages because of that. And also we see there is increased food prices. Increased food prices, those were the impacts. Right, then we look at our last question in a paragraph of approximately 8 lines. Suggest strategies how farmers can prepare for a drought. How can farmers prepare for a drought? Right, we can look at planting drought-resistant crops, drought-resistant varieties, crops and breeds. We are looking at the type of crops like the small grains, which ultimately resist drought conditions. And also we are looking at improved varieties which are drought resistant. Then also we look at building dams. They can also try to build dams so that they can have water for irrigation purposes. We can also have water storage, store water in JoJo tanks. And also we can look at use of awareness campaigns so that people are equipped with the knowledge of how to conserve the water resource. So awareness campaigns can also help. And also we can look at farmers taking initiative to plant trees. And also we look at the other measures that can be used, like reusing rainwater, right. That is what the farmers can do to try to help the situation of a drought. But there are also many other things that we can mention, which are in line with how farmers can effectively deal with the situation of a drought, so that they can try to resustain in the difficult situation. That was question number 1. We've come to the end of our question number 1 out of 60 marks. Right. We move on to question number 2, which is our question on geomorphology. We want to try and analyze the given questions under geomorphology, which is our question number 2 for theory under section A. Right. Our first question is a matching column question. The first question is saying layered rocks. Which component emerges with layered rocks? Are they massive igneous or are sedimentary rocks? We understand that our rocks which are layered are sedimentary rocks. Sedimentary rocks are made from sediments which accumulate and end up cementing and forming those layered rocks. So ultimately, sedimentary rocks, they are made up of layers because of the accumulation of sediments. Right. Then number 212, it says landforms that consist of rounded hills. Landform that consists of rounded hills and gentle slopes and form in warm or humid areas with high rainfall. Right. We are talking about rounded hills here. Automatically, we are looking at hilly landscapes. Those are typical landforms that we find with rounded hills. And they do have gentle slopes when they form in warm and humid climatic regions. Where there's high rainfall, there's dominance of chemical weathering, which results in the formation of gentle slopes. But where we have dominance of physical weathering, we tend to have find those hilly landscapes with rugged slopes. They won't have gentle, smooth slopes, but they will be having rugged slopes because of the nature of weathering that takes place. Right. Then number 213, it says a landscape that develops out of canyon landscapes and consists of landforms like mesas, the buttes, and conical hills. Right. What typical landforms are classified under the collection of the mesas, the buttes, and the conical hills? That is typical of the Karoo landscapes. I understand we know the distinction there between those landforms, a mesa, which is weathered down to a butte and weathered down to a conical hill. Right, vertical erosion is dominant and form deep valleys, steep-sided. What kind of landform do we experience? Do we have when we have vertical erosion dominating, resulting in the formation of deep valleys, which have got stepped sides? That is a description of a canyon landscape. Right, number 215, it says a canyon in an area with a humid climate. An area with humid climate and an area with dry climatic conditions. So in this instance, we want to analyze and look at a canyon landscape that is experienced in an area with typically humid climatic conditions. So by looking at our two illustration, we can see that typical of areas with humid conditions, the typical landforms that we tend to find that tend to develop, we tend to have the development of typical Z. All right, we move on to question number 216. Question 216, it says, mesas and baths commonly are found here. I think that is almost a similar question. Where we find mesas and baths, we find them in the Karoo. In the Karoo, that is where we find those typical landforms, the mesas and the baths. Erodes very fast. Which one between the two erodes very fast? He had layers and soft layers. We understand that soft layers are the ones that erode very fast because they have got weaker resistance to erosion. They tend to be affected easily by erosional processes. Right, number 218, it says the Drakensberg Mountain is an example of a. If you check at Drakensberg Mountain, the top layer is made up of a hard and resistant rock and is covering a less resistant rock. That is typical of a basaltic plateau. And also, if you check, the top part is flat. That is why we are saying it's a plateau. Right. Number 2.1 comes to an end with question 2.1.8. Let's look at question 2.2. But question 2.2 is a multiple choice question. The first question is saying tilted rock strata form in dash rocks. Where do we find tilted or inclined? Tilted is the same as inclined. Which rocks are likely to be inclined out of geomorphologic forces? If we have forces operating in the Earth's crust, they are likely to twist or to tilt those rocks. That is experienced in areas with sedimentary rocks. Landforms labeled R, R dash, and the slopes at P. We want to look at landform R, this particular part here. We are looking, this is an inclined strata. It's a landform made up of inclined strata with a scarp slope on one side and a deep slope on the other side. And also we are seeing the slope at P. This is the steepest slope of the incline. That is our scarp slope, and Q becomes the deep slope of our landform. So by mere looking at the responses there, we are saying our landform is a Kester, which is an inclined landform, and our P is the steeper part of our slope, which constitutes to be the scarp slope. So we are saying it's item number 1 and item number 3, which is our correct response, which is A. So you must remember the scarp slope is the steep one. So the scarp is the one which is here. The scarp slope is the one which is here. And then the deep slope is the one that is on that other side. That is basically how the slopes are inclined on a Kester. The scarp is the most steep, and the deep is the one which is general. Right. Number 2.2.3. The general slope that forms on a resistant rock strata is known as a dash slope. We are looking at the general slope. We have talked about that. That is a deep slope. Number 2.2.4, it says the dash has a steep deep slope and a steep scarp slope. We are saying this kind of an inclined landscape has got both a steep scarp slope on one side, and also the deep slope is also steep, something like this. This is our scarp, it's steep, and also our deep is not very general. You can see it's steep. What kind of inclined strata is this? This is typical of a Hawksberg. A Hawksberg is the one that is the steepest, that is with the steepest slope. So it's a Kester, then we go to a homoclinal ridge, then we go to a Hawksberg. A Hawksberg is the one that has got the biggest slope angle here. The slope angle for the Hawksberg is ultimately bigger, meaning to say the steepness of the deep slope is also pronouncedly very steep. Right, number 2.5, it talks about a Kester basin. In a Kester basin, the deep slope faces, does it face inwards or it faces outwards? The deep slope, when you're looking at a Kester basin, and dash, the deep slope faces dash, therefore it forms a what kind of a shape? Right, so if you are looking at a Kester basin, we are looking at a situation whereby our landform must resemble a basin. So for our landform to resemble a basin, it's the opposite of a dome. So automatically we are saying the deep slope in this instance must be outwards, and our shape must be, they must give a shape of a basin, because we are looking at a Kester basin. So it must form for us a basin, and our deep slope must be outwards. So our correct response is item C. Number 226, it says the dash slope of a Kester favors well-drained farmland. Which part of the Kester which favors well-drained farmland? Automatically, that's the deep slope. Right. Number 2.2.7, it talks about a homoclinal ridge. Homoclinal ridge is developed due to what causes the development of homoclinal ridges. These typical landforms which are inclined, they are as a result of the process of folding or the process of faulting. When we have those typical processes happening within the Earth's crust, they result in the tilting of the horizontal rock layers, and they will end up becoming inclined. Right, we go on to question 2.3. Refer to the figures below and answer the questions that follow. We have those three figures, figure A, figure B, and ultimately our fig C. Right. Our first question is saying, the intrusive landform at A is a batholith or a laccolith. The intrusive landform at A, this one here, can we say this is a batholith or that is a laccolith? That is automatically a batholith. What differentiates that is the shape of the landscape of the feature, and also its size. That is a massive feature. It's very big in size, which resembles that is a batholith. Right. When A is exposed on the Earth's surface, it will appear as, when you're looking at A, if it ultimately finds its way being exposed after all these layers have been removed, how does it going to look like? What kind of a geographical feature will it resemble? It is going to resemble a granitic dome. If you look at the shape, our domes, they look like something like this particular shape here, which is also a resemblance of the shape of the same intrusive landform while it is still underground. Our dome is going to look like something like this, and it's also going to be a massive feature. So if this is going to be exposed, we see the same shape being portrayed by A here. So it's going to give us a granitic dome Once it is exposed, it gives us a dome. Right. Then it says name the landform at C. At C, what kind of landforms are these? These are what we call the granitic tores. These are the tores. Describe how climate has an impact. Describe how climate has an impact on the formation of landform C. We are looking at climatic conditions. How do they facilitate the formation of the tores? Right. I'm going just to summarize. That is question number 1.2.3.4. Right. We're looking at the impact of climate on the development of the tores. How does climate influence the development of the tores? Right. So that is question 2.3.4. Right, well, let's look at cold climates. In cold climates, on cold climatic areas, we have typical frost action happening. Frost action is dominant in cold areas. Areas where temperatures fall to freezing point, we have the issue of frost action. What is going to happen? Water collects in cracks. And then during the night, it freezes and expands. Because of the excessively low temperatures, the water that is collected into the cracks is going to freeze and is going to expand. And as it expands, it gradually widening the cracks. That is basically what happens in areas of cold climatic conditions. Our granitic tores are going to develop further through the process of frost action, whereby water is going to collect in the cracks, and because of the low temperatures, the water freezes, it expands, it gradually widens the cracks until they appear as core stones which are balanced. And also let's look at humid conditions in areas with high rainfall. In humid tropical climates, we have chemical weathering. Chemical weathering is more significant in this region. And our main types of chemical weathering, we are mainly interested in hydrolysis and oxidation. Due to high temperatures and moisture. Right, so we are saying for the reason of having humid climatic conditions, like in the tropical climates where we have higher temperatures and abundance of moisture, we also tend to find that chemical weathering plays a significant role in developing or impacting on the formation of our granitic tores through hydrolysis and also through ultimately oxidation. Those processes are facilitated because of the high temperatures and the presence of moisture. Right. Let's go to the next question. The next question says, describe the formation of landform C. Describe the formation of granitic tores. How do the tores develop? That is question 2.3.5. Right, this process starts with an intrusion. When there's volcanic activity, when there's intrusive volcanic activity, we see that the hot liquid rock finds its way into the Earth's crust and cools. So we have cooling of igneous rocks below the surface. Why we are saying it's an intrusive in landform initially is because it forms below the surface. The hot liquid rock does not find ultimately a way to escape out of the Earth's crust, but rather it cools and solidifies below the surface. That's the initial step. And after solidifying below the surface, the cooling process causes contraction. There's contraction of magma. Remember, if it's hot liquid rock, it will be in an expanded form, and once it cools, it contracts. And that change from an expanded nature to a contracted nature, it results in joins. It causes joins to develop. Right, we are seeing the development of joins there. And then what is going to happen to the joins? We now have seeping water. Into the cracks and the joins. The joins were developed because of the cooling process, but now we are having seeping water, which is now getting to contact with the intrusive feature. And now the water is now seeping into the cracks and joins, and it results in weathering. Right, what is going to happen after that? We have surface erosion. The surface erosion results in cracks and joins to enlarge. So it results in enlargement of cracks. When there's surface erosion, we are saying the material that has been weathered is now being removed, and hence it is now widening the joins and the cracks. And also we look at the groundwater now. How does groundwater play a role? Groundwater, it dissolves minerals in the rocks underground. And ultimately, how does our landform come to existence? How do we come now to realize that we have granitic tuffs in a specific area? Because we said it's an intrusive landform. Ultimately, there is now the removal of overlaying layers. It now exposes the core stones. That's basically how our granitic tuffs come to exist. They start by the cooling process of magma underground, and the cooling process results in the development of cracks or joins. And then we have the influence of seeping water into the joins. We have the issue of chemical weathering taking place. We also have the influence of ground surface erosion, the dissolvement of minerals by groundwater, and ultimately the landform is going to be exposed as core stones. Right. Explain how future climatic changes affect the rate of formation of landform C. Future climatic changes affect. We want to highlight how future climatic changes can have an implication on the development of the the rate of formation. Right, let's look, for example, with increased rainfall. If in future there is increased rainfall, or if there is increased temperature, how are they going to affect? This could enhance chemical weathering. And erosion. And ultimately accelerating degradation. So ultimately we are seeing the influence of rainfall and temperature. They would speed up the process of chemical weathering and ultimately are accelerating the degradation process, which leads to fast formation of the granitic tuffs. And also, for example, if the climate is also going to change to a colder climate, what is also going to happen? A colder climate could increase the freeze-thaw action. How does that impact? Promoting new thaw development. So ultimately, we are also seeing the influence of the cold temperatures. New thaws are likely to develop because of the cold conditions, whereby accumulated water in cracks will freeze and will widen the cracks and ultimately lead to formation of new granitic thaws. Right. That was question 2.3. Let's look at question 2.4. Question number 2.4, it says, start the fig below and answer the questions. 241, the landform illustrated in the fig is associated with what kind of landforms? Is it a tilted or is with a horizontal sedimentary rock layer? Right, by our analysis there, you can check to see. You can figure out that this is a landform which results from horizontal sedimentary rock layers. Horizontal sedimentary rock layers are the ones that are facilitating the development of such landform. Number 2.4.2, it says, name the main slope elements, element V, element W, element X, and element Y of the slope. These are parts of the slope that we are supposed to label. So our item V, we are seeing that's the uppermost part of our slope. We call this the crest. And as you are coming from the crest, going down towards the general slope, this is a vertical. We can check here. It's a perpendicular slope, a vertical slope, part of the slope. We call this the cliff, or it is called the free face. Then now we are getting to our midpoint of our slope, where we have accumulation of material coming from the cliff. This is what we call the talus, or it's called the debris part of the slope. Where we find, you see this material here is material which has been weathered and which has found its way down. And then we have the general part of our slope, which is the lowest part of our slope here. This is what we call the pediment of the slope. Right, so those are our labels, starting with the uppermost part here. This upper bended part is the crest. Then the vertical one is the cliff. Then this slope where there's accumulation of weathered material from the top is called the talus or the debris. Then the pediment is the lowest part of our slope. Right. Then we move on to question number 2.4.3. Question 2.4.3, it says, using the diagram, describe the changes in slope gradient from V to Y. We are looking at the crest to the pavement. Right, let me use a space to ultimately explain how the slope changes. So we are saying our illustration looks like this. And then we have the debris slope. And then we have the pavement. So we are saying we are starting from here, the crest. And from the crest, we go to our free face. And then we go to our debris slope. Then we go to our pavement. The question says, use the diagram to describe the changes in slope gradient. From point V is here, and our point Y is here. So how is the gradient changing? Starting from the upper part, we are saying the uppermost part of the slope, uppermost part of the slope is at V. I think we can see that that's where the highest point of our slope, where our slope is starting. Then what is the gradient? We have steepest gradient. At W. And at W there is almost vertical. It's a vertical slope on the free face here. That's the steepest part of our slope. And then as we go down, we have to face a slightly less steep, slightly less steep, concave slope. Our concave slope, we find it on the debris, which is our X. So we are seeing that the accumulation of material there leads to a slightly concave slope, because you are having accumulation of finer material. It creates a concave shape. Then as we go down, we reach the almost flat. Or we can say this is the gently sloping area at Y. And why is it gentle? There is evidence of deposition of material there. We have a flat or a gently sloping landscape at Y, which is the pavement, because of the deposition of material. All right, that is basically how we can describe our slope from the onset of our feature to the bottom. Explain why slope elements at Y is favorable for farming. Why is the pavement here favorable for farming? Right, the reason there is we have fertile soil. Where does the fertile soil come from? It comes from weathered material from the top of the slope here. The finer material is going to be deposited here. So we have fertile soil for crops. It's a favorable factor. And also the slope. There is a gentle slope for easy cultivation. So it's favorable for agriculture. Why? Because it's not steep. If you are comparing it to the talus or the free face there, we cannot do any agriculture. Why? Because of the nature of the slope. But as we go to the pavement, it's almost flat, and hence it means it makes it easier to cultivate. There is easy cultivation which can happen there, and also the soil is fertile because it's made up of weathered material from the upper parts of the slope or the upper reaches of the slope, which are deposited at the bottom part. Right, then number 245, why does the angle at the slope element X develops changes constantly? Let's look at X. We are looking at the talus here. We are saying it changes. Why does the angle of the slope element X develop changes constantly? Right, we'll just try to summarize why it develops changes. Element X here is a transition. Is a transition zone between steep debris accumulation above and the flatter deposition below. So we are seeing it's a zone of change from this steeper part with accumulated material and the bottom part here. So it means it cannot maintain the same angle. Why? Because it's not a permanent, it's a transitional zone. It's a change from steep debris accumulation and flatter deposition at the bottom of the slope on the pavement. So there's interplay between material added from above and material removed from below. So we are also seeing why we are saying it's a transition, because there can be more material being added from the top. And at the same time, there's also material being transported downwards. So this angle does not remain the same. Why? It depends on the balance of how much was added to the slope and how much has been lost from the slope. Because as more material is being added from the top, there is also loss of material which is being transported to the pavement there. And also, we can look at other impacts like environmental conditions. For example, rain. Environmental conditions, e.g. rain. Or we can look at freeze-thaw action. Or even vegetation. Also allow the slope to change. If there is heavy rainfall, ultimately it facilitates transportation of material from the talus slope, and it is going to change its angle because more material is going to go to the pavement, and then the angle is going to be affected. Or if there is thawing of the ground, we tend to find that the material that makes up the slope is moved downwards, and that is going to change the angle. Or also vegetation. If there is vegetation, it can stabilize the angle of the slope, but if it's removed, then there will be more erosion taking place, and ultimately the material eroded is going to ultimately change the nature of the slope of that part. That is why we say that element develops changes constantly. It does not remain stable, but it rather changes. Right. That was question 2.4.5. Let's look at question 2.5. It's massive rockfall blocks road in Cape Town. That is a case study of Cape Town of rockfalls. Right. Our first question, it says, define the term mass movement and define this geographically as mass movement is the movement of soil, loose material or loose stones, and rocks down a slope. That is general definition of mass movement. The movement of soil material, loose stones, rock material down a slope under the influence of gradient. Name the type of mass movement in the infographic. Our infographic here is telling us that there are rockfalls. Massive rockfall blocks the roads. So our is rock falls. Right. Then it says number 253. Refer to the text and explain the cause of the mass movement on Table Mountain. What is the cause according to the text? Right. If we try to figure it out there, you can see that the rockfall is as a result of natural erosion of the shell rock. So this is where we find our response. The rockfall is as a result of natural erosion of the shell rock. That's the cause. Natural erosion of the shell rock. How did the local government of Cape Town reduce impact of mass movement in the infographic? Let's look at what the government of Cape Town did to try and reduce the impact. Right. So, according to our information there, we are seeing that the government has tried to find a way of trying to deal with the problem, trying to reduce the impact of the mass movement. If we check here, and also we can see here what has been done. If we check, they've installed canopies here to cover the road. And also if you check here, there's concrete impact protection on this side here. So those are some of the measures that we can talk about. So they are saying they have adjected a rockfall canopy adjacent to half the tunnel. And also if you see there's usage of concrete impact protection on that particular part. So our response, we can say the local government there has introduced a canopy, a concrete canopy to cover up the tunnel, or can say they have applied a concrete impact protection canopy to reduce the impact of the rocks falling on the road. They've put a canopy to cover. Then our question 2.55, it says, in a paragraph of approximately 8 lines, describe the causes and characteristics of mass movement. we want to look at the causes and the characteristics of mass movement. Right, so basically our mass movement, what makes loose material move down the slope? Basically, the causes which are common, we are looking at water. Usually in the event of heavy rains, they tend to facilitate mass movements. And also, the other cause, areas which have got steep slopes, is a factor that favors the movement of material down a slope under the influence of gravity. So the implication here is if we're having heavy rains, the rainfall is going to act as a lubricant on the material and is going to slide down the slope. And also the rainfall is going to add weight to the landmass such that it becomes heavier and unstable and tends to move down the slope. Then also, if your slope is steep, it facilitates the flow of a material down the slope. And also, we need to look at the features. Here, we tend to find that when we're looking at mass movement, we are looking at factors like high speed of the mass movement. If an area is steep, it is going to cause mass movements which are more destructive. Why? Because the material is going to move at a higher speed. Or if the level of saturation by rainfall is high, it also means the material is going to be heavy and is going to be moving at a faster pace. Right. Then we also look at other causes like weathering. We've looked at rockfalls. Rockfalls, usually they are caused by the weathering processes. If rocks are weathered and are detached, they are broken down. Automatically, it means the rocks are detached from the core main rocks and they tend to fall. That is going to result in instances of rockfalls. Then also, if you look at vegetation loss, if we deliberately remove vegetation on steep slopes, ultimately we are destabilizing the slopes. And that is going to ensure that the slope becomes unstable. And once the slope becomes unstable, that is going to facilitate the movement of material under the influence of gravity on those slopes. Why are we talking about vegetation? We look at vegetation roots. The roots are essential. Vegetation roots are essential for stabilizing the slope. They bind material on the slopes. So if we remove vegetation, it means we are destabilizing the balance there. Then also, if you are looking at the characteristics, because our question is saying the causes and the characteristics. Under characteristics, we can talk about the nature of the movement. Of the movement in terms of speed. Right, our mass movements, they tend to differ in terms of their nature of movement or in terms of the speed. We have fast moving, like for example, rockfalls. They are fast. Then you also have slower mass movement processes. Like you look at soil creep, it's a very slow movement. Or you compare rockfalls with mud flows. They are slightly different in terms of the nature. And also, it also implies that in terms of the impact, mass movement, they also tend to differ in terms of their level of impact. Some are very destructive. They destroy vegetation along, they destroy habitats. They also cause very serious environmental harm. Like, for example, if you look at avalanches or if you look at even the rockfalls, they are equally destructive. But some are less destructive. Like, for example, the soil creep is a very slow movement, which ultimately can cause little damage. Like, we can see evidence of cracks on the roads, or we can see the leaning of trees, or we can see cracks on the ground, which is evident, but the destruction is minimal compared to the destruction by fast moving mass movement processes. Right. Basically, that's the picture of what we needed to address for that particular question. And that takes us to the end of section A. We're going to look at our section B, but we're just going to highlight on the discussion of common questions. For this discussion, our map is not available, but we'll just try to highlight on how you are supposed to figure out the responses from the common questions. Right. There is our map. It's a background information on Melelane. And the location of Melelane is shown there on the map, and it gives us the information. Right. That information is essential. You must use it. You must go through it to help you to answer some of the questions. Right. The first question is saying, in which province is Malelane? According to the map information, this is a location in Mpumalanga province. Then it says the map index or reference of the map northwest of Malelane is. We want to find the map index of a map which is to the northwest of our map in question. I think you understand how you do your map referencing. You have to check your map reference for the particular map, and then you are supposed to allocate the other blocks in terms of their references, so that you are able to figure out the actual reference of a map in a given direction. So what you must note on the map reference, let me just use A as my example. Since you don't have the map, you must interpret the meaning of the reference 2531 AD. You must be able to interpret the meaning of this so that you are able to do the allocation of the other blocks and be able to figure out. So it means this map is a map along the 25 degrees line of latitude. And in this instance, for South Africa, we are to the south of the equator. And our 31, it means this map is in the block of 31 degrees latitude, longitude. And our direction is always to the east of the prime meridian. Then we do what we call subdivision of the blocks. The main block is subdivided into 4 bigger blocks. Then the bigger block again is subdivided into smaller block subdivisions. That is where we're getting these letters. So the first letter represents the bigger block subdivision, the first subdivision of our grid reference block. Then we also subdivide them into smaller 4 for each. Right. So you are supposed to figure out sense and be able to figure out how we do the referencing there. The index of the orthophoto map showing the recreational area in block B2. Again, we cannot do that. We're supposed to check on the map and look at the reference of the orthophoto map. Right. Calculating gradient. That is common understanding. I'll just explain what you need to do. When you're calculating gradient, we are supposed to figure out the gradient between a spot height and a spot height in another block. So what we mean here, we are saying you have to identify your two features. Let's say the question is saying calculate the gradient between these 2 points. There's point A, which is a spot height here, and maybe there's point B, which is also another spot height. So what you need to do here, your gradient, you use your formula. It's vertical interval over horizontal equivalence. So you must understand these two aspects on your formula. Vertical interval is difference in height. between the points. The points in question is a difference in height. Then our HE is the actual ground distance between the 2 points. So let me just use a simple illustration. Let me say this is a higher point, is 1,140. This spot height, and this one is 1,100 and let's say 20. Right, these are my 2 points, and when I want to calculate the vertical interval, I'm saying all heights that I see on the map, they are already in meters. So this is 1,140, it's in meters. This is 1,120, it's in meters. So if I'm supposed to get my VI, I'm just saying the bigger figure, 1,140, it's in meters. I subtract 1,120, which is also in meters. I get my answer in meters as 20 meters. That is my VI. Then I now go to calculate my HE. My HE, I am saying this is an actual ground distance between the 2 features on the map. And I am assuming that here I am using my topographic map. If I'm using my topographic map, it means I have to always remember that the scale for the map is 1:50,000. So what I need to do to find actual ground distance, I have to measure the distance between the 2 points. Measure the straight distance between these 2 points. Let me say in this instance, these 2 points are 5 centimeters apart from each other. You measure your distance in centimeters from the starting point to the end point. You identify your distance on the ruler. Let me just use this as an example that my distance is 5 centimeters. How am I going to get my HE? I am now saying my measurement is 5 centimeters. I need to convert this according to the scale of the topographic map, which is 1:50,000. And remember what I need to do here. I need to make a fraction with the value of VI, which is already in meters, versus the value of HE, which must also be in meters. So how am I going to convert a scale of 1:50,000 to convert the actual ground distance into meters after finding out that the distance on the map is 5 meters? I will have to simply multiply my centimeter measurement by 500 to convert the distance on the map to the actual ground distance to give it in meters. So I'm multiplying this by 500 meters. So this is going to give me 2,500 meters like this. So it means now this is my HE. So I now make my fraction because my formula is saying VI over HE. I now have my 2 figures. What is my VI? My VI, I got it there as 20 meters. And what is now my HE? My HE already again is there also in meters, which means I have simplified what I need to deal with because I now have the same units of measurement to use for the sake of making a fraction. Right, so it's 20 meters for VI, and for HE is 2,500 meters. And automatically my meter is going to cancel with my meter. Then I remain with 20 over 2,500. Right, our gradient, remember, must be expressed as a ratio with a numerator equal to 1. That is the rule of gradient. We must always express our gradient as a ratio with a numerator equal to 1. So my numerator is 20 here. I need to reduce 20 to 1. What must I do? I divide it by itself. Then I also do the same to the denominator. I divide it by 20. After dividing this, it gives me 1 as the numerator. And after dividing this, it gives me 125 as the denominator. So as a ratio, I'm saying my gradient is 1 as to 125. That will be my final answer for the sake of just an illustration. Right. Then it says refer to the answer and describe the steepness of the slope. How do you describe the steepness of the slope? If you want to describe the steepness of the slope, the meaning of this is, if you are to use a triangle, we are saying this is your vertical interval, this is your horizontal equivalence. If you are to use this illustration here, right. So we are saying on this side here, we must have our vertical interval, which is 1 meter. So we are saying for every 1 meter rise, what is the compensating horizontal equivalent for that particular 1 meter that we have realized on our illustration here? So it means our compensating horizontal equivalence must be longer. We are comparing 1 meter to 125. So what is the nature of the slope? If you are to do it justifiably, our 1 meter must be shorter, because we are comparing only 1 meter to 125. So which means this might be our vertical interval and our horizontal equivalence is there. So if you are to join this point, if this is our 125 meter mark versus our 1 meter mark here, how is the landscape going to look like? It's going to look like something like this. So it means this is a gentle slope. But let's assume our gradient was 1 as to 10. If we found our gradient as 1 as to 10, was it going to look the same? No, we are comparing 1 meter versus 10 meters. 10 meters must be shorter. So we are seeing, if it was like this, our slope was going to be steep slope. So whenever you're interpreting your gradient, check the denominator. If the denominator is a smaller figure, it means it's a steep sloping landscape. And if our denominator is a bigger figure, it means it's a gentle slope. And also by merely looking at the map, you check also the contour lines between the 2 points. If these are our 2 points, and you see that from there, there's a contour line here, and there's another contour line there, and maybe another contour line is seen here. These contour lines are far apart. What is the suggestion? They give us an indication that the area is gently sloping. But if it's a steep sloping area, it will mean that if you are having point A and point B, we are going to see our contour lines as close to each other as is possible between the 2 points. So it means this is an implication of a steep slope. Right, just for clarity purposes, let's go on and look at the other questions. Right, refer to the background information and describe the climate of Melilane. If you look at the background information and try to relate to the climatic conditions, we see that Melilane has got typical of subtropical climate. Remember, South Africa is predominantly in the subtropical climatic region, whereby we have typical conditions of humid summers and some mild dry winters. Right. So basically, that's the idea of how we can apply. But unfortunately, because we don't have our maps, we cannot be able to elaborate much on some of the aspects there. But if you look at question 3.22, which says, refer to block E2, how the farmer south of N4 implemented sustainable strategies to prepare for possible drought. If you check there, you will find that if there's evidence of dams, it's a strategy to deal with the drought situation, or if there is evidence of wind pumps, it's also a strategy to extract groundwater to deal with the problem of water shortages. That is what you need to check there. Right. Then it says, refer to the trigonometric marker 145 in block C2. Describe the relationship between altitude and air pressure. Describe the relationship between altitude and air pressure. We understand the relationship there is that the higher you go, the lower the air pressure. The lower the air pressure becomes, which means in upper atmosphere, the concentration of air molecules is limited. There is less air pressure. Then it says, number 234, identify the structural landform indicated by line A. We want to look at line A to B. If you look at from line A to B here, what kind of a structural landform is resembled by that? So if you check here, you can see that from this point going towards A, this is a steeper area. Why? Because the contour lines are close to each other from this point. But starting from this spot height going to B, the contour lines are spaced further apart compared to this part. So which means the shape of this landform, if you are to put it in your cross section, it is going to look like somewhere the spot height is 1, 4, 3, 4. Then from the spot height, we have a steeper slope going towards A, which means our A is somewhere here. Then going to B, you see that the slope is general because the contour lines are further apart from each other, getting to B. That is the shape of this particular landscape. So what kind of a landscape is this? This is typical of inclined rock strata, which can be a castor. Or we can basically say it's a homoclinal ridge. Right. Then the next question is saying, name the rock type that is mainly responsible for the development of this kind. We've talked about that in earlier discussions. That is typical of sedimentary rocks. They are the ones that facilitate the formation of inclined stratus. Right. Draw a freehand cross section from A to B and label the slopes. I think we've already done that. The slopes that we only need to do label here is we need to label the scarp on this side, and you need to label the deep slope. So if it's just a cross section, we're just drawing a line like that to show that on this side there is a general slope going upwards, and our highest point is somewhere there where there is that spot height. Then we come down towards A like that. That is the shape of our landscape. Right. Then we move on to GIS section. The first question says the component A in the illustration above is component A. We are seeing A there. That is part of the software. Compare B in the illustration above. Component B in the illustration above is, what is component B? We are seeing these guys there. Those are the personnel or the people. Right, then it says Refer to block E1 on the topographic map. Unfortunately, we don't have the map. Right. What is our area of concern? The question is saying, what is the difference between raster and vector data? Right, raster data differs from vector in terms of how the data is presented. So raster, it uses grids or it uses pixels. Then vector data, it uses lines, points, and also uses polygons. That's the distinction there. Then it says identify a polygon feature in block D1. Typical of any feature that has got an area, a feature which is enclosed. For example, you can look at cultivated land. If there's any cultivated land, it's an area feature, it's a polygon. Or if there is, for example, perennial water or a dam. Or if, for example, there is also a nature reserve, it's an area feature. A recreational ground can also be an area feature. A sports field, anything that has got area is a polygon feature. Right, refer to diagrams A and B. Resolution refers to the detail to which a map depicts the location and shape of geographical features. Which diagram A or B has got better resolution? Better resolution, we are looking at the clarity or the amount of detail. This one is better. We can actually see the features. They are more clearer. This one is a worse resolution, not even clear. Give a reason for the difference. Why is this one visible and why this one invisible? The difference there comes with the size and the number of the pixels. So in A, for it to have high resolution, a high resolution image will have smaller pixels that make up the image, and also they must be many of them. So it means for an image to be clear, it needs to have very small pixels and there must be many. But for B, if you check, this is a low resolution image. It's actually not even visible. What is happening with it? It has bigger pixels. The bigger the pixels, the lower the resolution. And it has fewer pixels. So if pixels are limited in terms of number and they are big, they give us a blurry image, which is not visible, which does not have clarity. So our clarity here is what we are referring to as to resolution. The amount of detail that can be detected on the picture. We can actually see from diagram A, but from B we cannot see. Why? It's a low resolution. Where does the low resolution come from? It comes from the size of the pixels and also the number. So the bigger the pixels and the fewer the pixels, the lower the resolution. Smaller pixels in large numbers, they give us a clear picture, which is a high resolution image. Right. I think that is our part on GIS. That was the conclusive part on our geographic information systems. Right. So with that being said and done, I think we have come to the end of our discussion. And I think this discussion is also going to ultimately help you as you prepare for your upcoming examinations, whether be it the June examinations for those who haven't written, or for your paper one end of year examinations. It's still the same scope of coverage of topics which are going to be examined in paper one as per the sample of the June examination. Thank you for watching. Your host in Geography. We'll meet again in other upcoming discussions.
Welcome to Thundereduc, an online learning platform powered by professional, highly skilled and qualified educators.
We deliver structured CAPS online lessons for high school subjects, including mathematics, physical sciences, life sciences, geography, business studies, history, accounting, English, Afrikaans, and others.
For the intermediate and senior phases, we offer expert teaching in natural sciences, mathematics, social sciences, English, and EMS, designed to build